Welcome to sample preparation. So sample preparation is the process of transforming a sample into a form that is suitable for analysis. The sample preparation may involve extracting the analyte from a complex matrix, pre-concentrating a very dilute analyte to get a concentration that's high enough to measure, masking or removing interfering species, derivatizing, so chemically transforming, our analyte into a more convenient or more detectable form. So note that sample preparation is discussed in detail in Chapter 27. In this section, we're only going to focus on sample preparation techniques that are particularly relevant to gas chromatography and not other types of analyses. So solid phase microextraction is able to extract compounds from liquids, air, so gas phase, or sludge without using any solvent. This is accomplished using a fused silica fiber coated with a film of 10 to 100 microns thick of stationary phase similar to that used in a chromatography column. And the fiber can be retracted into the needle. So we've got our fiber here in blue, our needle there, and so we can retract this fiber into the needle or bring it out of the needle to expose it to some environment. So to analyze a solution, the needle is inserted into our solution here. The fiber is then extended out of the needle, exposing it to our solution. The solution is typically stirred and may or may not be heated. And after some time, then the fiber is retracted into the needle, and the needle is then removed from the solution. The wait time is best determined by experiment. The wait time should be long enough for the fiber to become saturated in the analyte. If a shorter wait time is used, then repeated trials will have significant variation in the analyte concentration on the fiber. And note that the procedure for analyzing gas in a headspace above the liquid is similar to that which we've described already, only you're not exposing that fiber directly to the liquid, you're only exposing it to the gas above the liquid. So to analyze the analyte that is absorbed into the film on the fiber, then the needle is inserted into the injection port of our gas chromatograph. The injection port should be in splitless mode. The fiber is then extended into our injection liner where it's hot, and the analyte is then thermally desorbed from our fiber. And then the analyte should be collected on the column using cold trapping, which was discussed in section 23.2. Now, the mass of the analyte, M, in micrograms, absorbed into the film on the fiber is given here, where VF is the volume of the film on the fiber, VS is the volume of the solution being extracted, C0 is the initial concentration in micrograms per milliliter of the analyte in the solution being extracted, and K is the partition coefficient for our solute between the film and the solution. So recall that the partition coefficient is CF over CS, where CF is the concentration of the solute in the film, and CS is the concentration of the solute in the solution. So if a large volume of solution is extracted such that the volume of the solution is much larger than K times the volume of the film, then the equation reduces to N equals K times VF times C0. That is, the mass of solute extracted is proportional to the concentration of analyte in solution. And this means that we can perform a quantitative analysis. A calibration curve can be constructed by extracting from solutions of known concentration. Alternately, internal standards or standard addition could be used here. Another technique called Stirbar sorptive extraction is similar to our solid phase microextraction. However, Stirbar sorptive extraction is around 100 times more sensitive for trace analysis. So a magnetic Stirbar is enclosed in a thin glass jacket and coated with a 0.5 to 1 millimeter thick layer of sorbent, again a stationary phase used in a chromatography column. And the Stirbar is then stirred in our aqueous sample here and stirred for around half an hour to 4 hours to absorb our hydrophobic analytes in that stationary phase layer. So the mass of analyte extracted is given by the same equation as for solid phase microextraction, but the volume of the film, so VF here and there, is increased from the around 0.5 microliters used in the solid phase microextraction to somewhere between 25 and 125 microliters in Stirbar absorptive extraction. And thus, 50 to 100 times as much of our analyte is extracted with our Stirbar. The Stirbar is then removed from the solution, dried by lightly touching to a tissue, and perhaps rinsed with a few milliliters of water. The Stirbar is then placed in a thermal desorption tube, and the analyte is desorbed by heating the tube to around 250 degrees C for 5 minutes in a flowing carrier gas. The volatile analytes are collected using cold trapping. Now, analytes at parts per billion or even sometimes lower concentration can be measured using standard addition, isotopic internal standards, or a calibration curve constructed with the same matrix. Purge and trap is a technique for removing volatile analytes from liquid or solid samples, concentrating the analytes and introducing them into the gas chromatograph. Where solid phase microextraction removes a portion of analyte from the sample, purge and trap aims to remove all of the analyte from the sample. However, quantitative removal of polar analytes from polar matrices is very difficult to do. So, an apparatus for capturing volatile flavor components from soda is shown over here. The helium purge gas is bubbled through the soda in a vial, which is heated to 50 degrees C in order to increase the vapor pressure of the analytes. The purge gas then exits the sample vial up here and passes through an adsorption tube containing multiple layers of adsorbent compounds, so here, here, and there, with increasing adsorbent strength. In this case, those are phenylmethyl polysiloxane, tenax, and carbon molecular sieves. Now, during the purge and trap process, the purge gas flows through the adsorbent tube from A to B. And after all of the analyte has been purged from the sample and adsorbed in the tube, then the purge gas is flown from B back to A at lower temperature, so 25 degrees C, in order to remove as much water or other solvent as possible from the adsorbent layers. And then the adsorbent tube is connected via end A to the injection port of a gas chromatograph and heated to around 200 degrees C. Analyte desorbs from the adsorbent layers and is then condensed on the column using cold trapping. The column is then heated in order to initiate chromatography. Thermal desorption is a technique for releasing volatile compounds from solid samples. A solid sample of known mass is placed in a steel or glass tube and held in place with glass wool. The sample is purged with carrier gas in order to remove oxygen, and this purge gas is then vented to air, not flown into the chromatography column. Remember that oxygen will degrade our stationary phase of our column. The desorption tube is connected to the chromatography column and is then heated to release the volatile analytes, which are condensed on the column using cold trapping. And the column is then heated in order to initiate chromatography. And that was sample preparation.